Okay, in this video, we will be studying an orthonormal basis, which is a set of vectors, and each vector in this set is normalized. That is, the length is 1, the norm is 1, and each pair of vectors are orthogonal to each other. That means they are perpendicular to each other. And we will see how we can get an orthonormal basis from any given set of linearly independent vectors and how useful they can be. Okay, let's start. So first, let's consider a set of vectors x1, x2, and so on up to xd. So they are just arbitrary vectors. And in this video, we represent each vector with a letter with this wavy underline just to distinguish between vectors and their elements. Okay, so now consider this set M, which is made of all possible linear combinations of these vectors, D and Cj, Xj, and Cj. Each of Cj is a real number. So this is a set of all vectors that can be represented as a linear combination of these D vectors. So in this sense, we also write M of x1, x2, and so on. And we say these vectors are linearly independent if the following holds. The linear combination of these vectors is 0, if and only if all the coefficients are 0. Okay? Now, suppose that x1 up to xd are linearly independent. Let's write linearly independent. And suppose we have another vector y that is represented as a linear combination of these vectors. So let's say aj times xj. Now, if these vectors are linearly independent, then this representation is unique in the sense that if there is another representation, let's say bj of x times xj, then it is necessarily that each of these aj is equal to bj. So let's prove that. So suppose we have two representations of the same vector. Then from this being equal to this, from this we have the following. So aj minus bj times xj is equal to the 0 vector. So since we are assuming that xj's are linearly independent, that means if and only if this is 0 vector, if and only if each of aj minus bj is equal to 0. So j from 1 to d. So that means all of the coefficients are equal. Okay, so that means this representation is unique. Now, in the following, we always assume that this set of vectors x1 up to xd, they are linearly independent vectors. Okay? If they are not, we can just simply remove some of the vectors until all of the elements of this set of vectors become linearly independent. So without losing any generality, we can just assume that they are always linearly independent for some d. Now, suppose we have two linearly independent vectors. Okay, so x1 and x2, they are linearly independent. Then, another set of two vectors, let's say x1 plus x2 and x1 minus x2. So these two vectors are also linearly independent. And not only that, the set of all vectors represented as a linear combination of these two vectors is equal to the set of all vectors that can be represented as a linear combination of these two vectors. That means m, x1, x2, this set of vectors is equal to m, x1 plus x2, and x1 minus x2. So any element of this set on the left-hand side can be represented as a1 x1 plus a2 x2, right? So each of these can be represented as a linear combination of some linear combination of these two vectors. So that means we should have some b1 and b2. So that this equality holds. Okay, so let's simplify the right-hand side a little bit. So by adding b1 plus b2 here, x1, and b1 minus b2, x2. So from this, if we fix the values of b1 and b2, that will give a unique values for a1 and a2. So that means for each element on the right-hand side, there exists a corresponding element on the left-hand side, right? Now, if we solve this equation, a1 equals to b1 plus b2 and a2 equals to b1 minus b2. And if we solve this, let's see, how can we solve this? So b1 is equal to, so if we add this and divide by 2, a1 plus a2 over 2, and b2, subtract this, so a1 minus a2 over 2. So that means if we fix the values of a1 and a2, we can find a corresponding pair of unique values of b1 and b2. So that means for each element in this set on the left-hand side, there is a corresponding unique element in the set on the right-hand side. So they are, onto and one-to-one, so they are the same set. And the vectors here on the left-hand side, x1 and x2. On the right-hand side, x1 plus x2 and x1 minus x2. So these vectors are called basis of this set of vectors. Okay. So the basis of, suppose we have a set of vectors, and then the basis of that set of vectors may not be unique. Okay, so we can either choose x1 and x2 or x1 plus x2 and x1 minus x2. So the choice of the basis is not unique for a given set of vectors, but the number of vectors comprising the basis is unique. So if we have two vectors on the left-hand side, there must be two vectors on the right-hand side too, if we choose a different set of basis vectors. So that fixed number is called the dimension of the vector space. Okay. So the dimension of a vector space is the number of vectors in basis set. Now consider the following problem. Given a basis of d vectors, find another basis such that they are orthonormal. That means the inner product between EI and EJ is Kronecker delta. So that means, of course, 1, the inner product is 1 if I is equal to J, or 0 if I is not equal to J. Before giving the general method, let's consider the three-dimensional case, that is d equals to 3. So we have three vectors, x1, x2, and x3. And find another set of three vectors, e1 and e2 and e3. Okay, how can we do that? First, let's define e1 by normalizing x1. Okay, so x1 divided by the norm of x1. Then from here we can see that e1's norm, that is the inner product of e1 with itself, is norm squared. So this is equal to 1, right? Okay, let's check it. So E1 is by definition x1 divided by the norm of x1, and x1 divided by the norm of x1. So these constants can be put outside. So we have 1 over x1 norm and 1 over x1 norm. So we have 1 over x1 norm squared and x1 and x1. Okay? But the inner product between x1 with itself is the norm squared. So that is x1 norm squared times x1 norm squared, which is equal to 1. So we prove this. Next, let's define x2 prime by x2 minus the inner product between x2 and e1. So e1 is the vector we just defined here. And so this is a scalar and times e1. Okay. Now, e2 is given by x2 prime divided by its norm. From this, we can easily see that the inner product between e2 and e2 is 1, right? Just like we did here. Okay, so it's a vector divided by its norm. It's a vector divided by its norm, so its norm should be 1. Now, what about the orthogonality? That means e1 times e2. So what happens to this? Let's keep e1 as it is and put e2 as this. And give the definition of x2 prime. You know, we are interested in whether this is 0 or not. So just ignore this part and just use x2 prime, okay? So this is similar to, without considering the constant, e1. And x2 is this. So x2 minus x2 e1 and e1. Okay, so this is equal to, so we can expand this, and this times this, e1 times x2, minus, so this is a constant, so let's move it outside, and e1 times e1. Okay, but e1 times e1, this is 1, right? So this is equal to 1, and this is e1 times x2 and x2 times e1, and the inner product is commutative. So this is equal to 0. So e1 and e2 are indeed orthogonal to each other. Next, let's define x3 prime as x3 minus the inner product between x3 and e1 times e1, and the inner product between x3 and e2 times e2. Then e3 is given as the normalized version of x3 prime. Okay, and again, from here, it's immediate that the inner product between x3 and e3 and e3 is equal to 1. So that's clear. And what about e3 times e1? So let's see. So e3 is x3. So just ignore this constant term. So this is somehow similar to x3 minus x3 e1, and x3 e2, and e1. Okay, so let's expand this, and x3 and e1. We have this, and this thing times e1. So x3 constant out, and e1 and E1. Okay, so that will be 1. And finally, this times this, so that's minus x3 E2 times E2 times E1. And we know that this is equal to 1, and we know that this is equal to 0. So this will be gone. So we can just put it as 1, and x3 times E1, x3 times E1, so that's 0. So they are orthogonal. And similarly, we can see that E3 times E2 is also equal to 0 by similar calculation. So we have achieved finding an orthonormal basis starting from an arbitrary set of 3 vectors x1, x2, x3, and finally got E1, E2, E3. So this way of finding a set of orthonormal bases is called the Gram-Schmidt process. And for general dimensions, for general d dimensions, we do this. So we have first, we are given d vectors, x1, x2, up to xd. And for each L from 1 to up to d, we do the following. First, define xl prime as xl minus sum of this j from 1 to l minus 1, and take the inner product between xl and ej and ej. Okay, when L is equal to 1, this term is absent, but from L equal to 2 and upwards, we have some EJ already defined sometime by this process. So EL is just a normalized version of this. So XL prime divided by its norm. Okay, so by this process, we can find E1, E2 up to ED in this term, in this order. And they are just like we did for d equal to 3 case, we can show that these vectors are orthonormal to each other. That is, so this inner product EI EJ is equal to Kronecker's delta, delta IJ. So what's so important about orthonormal basis? The reason is that an orthonormal basis makes life easier. Okay, let's see an example. Suppose we have a vector space M that is accompanied with a basis set. So E1, E2, and ED. And these are assumed to be orthonormal basis. And then consider 2 vectors, x and y, belonging to this space. Okay, that means each of these vectors can be represented as a linear combination of these orthonormal basis vectors. So let's say x is aj times ej, and y similarly is another linear combination. Let's say bj and ej. Okay, so first of all, the inner product between x and ej is equal to aj because of orthonormality. So it's very easy to see. So just substitute the representation of x instead of j. Let's write I here. EI and EI. Okay, so that's equal to sum of AJ and EJ EI. But this is an orthonormal, so we have AJ delta IJ. But this Kronecker's delta is 1 only when I is equal to j. Otherwise, it's 0. So if this j runs from 1 to d, then only one of these j's is equal to I, so that becomes ai. And similarly, the norm of x, let's make it square to make it simple. So this is equal to, by the same calculation, similar calculation, we have this aj squared. So sum of aj squared. So sum of squared coefficients becomes the squared norm of x, of any vector. And next, consider the inner product between x and y. And if you do a similar calculation, we find that this is just the sum of the products of the coefficients, aj and bj. So aj times bj and sum over all possible j's, then that's the inner product between x and y. So these nice properties hold because of the orthonormality of the basis of this space and representation based on the orthonormal basis. Otherwise, this will become more complicated because there will be some cross terms between the coefficients of different vectors in the basis set. Okay, so that's all for this video. See you later. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.